So now stuff that isn't on the quiz. So let me finish off chapter 1. And in some ways, this is going to be kind of typical, which is if you're looking at my written notes, which I put on Blackboard, we didn't get all the way through the notes that I had from yesterday because I read them beforehand. And so therefore, we'll continue with notes that are actually on yesterday's notes. And it looks like we won't finish what I have written today. So I'll continue these tomorrow. So chapter 1 has 2 extra pieces. So let me go through those quickly. So the next one is 1.7. This really is, that's almost the word, functions of severable, wow. Functions of several variables. And that just means something like, now we can have it just means we can have more than one variable. And we can either have in the traditional form like this, or we can have a vector form. And pretty much in 1.7, they're just talking about, they're asking, saying how you might want to graph something like this and what it might look like. We're not going to make you graph it, and graphing sort of is a 1.8. So they also talk about domain and range. There really isn't anything new there. About the only thing is for the domain is just like if I have things like this, well, I can't divide by 0, so x, in this case, x plus y can't be 0. I can't take natural log of a negative number, so x plus y has to be more than 0. So I solve the same thing, it's just that it looks more complicated. But since we're not going to actually have you draw the domain or range or codomain or anything like that, all you need to know is the basic idea that, yeah, it might not be defined. So it means I might be restricting the types of numbers I can put in. And pretty much that's just 1.7. So 1.7 really is nothing except for this idea that we can have more than one variable. And so if you want to look at the homework, you can, but you don't have to do any of it. So there's 1.7. One 1.8 is in some ways a similar thing, is you don't really have to know it too much. We're not going to make you draw anything, but there are certain ones that come up a fair amount that you should know what they look like. So for example, you should know that right. So there's nothing in 1.7 that you need to know. It's just this idea that I can add more variables. I can still ask for domain and range and stuff like that, but we're not going to ask you for domain and range and stuff like that. So for example, what is this thing? That's supposed to be a z squared also. So this is here. And the radius is, as usual, the square root of the r squared. So it's x squared plus y squared plus z squared is equal to r squared. So now three-dimensional. Another one that comes up a lot is this. And I'll use this one to talk about what they're doing in this action, which is say what the graph might look like. So this is called paraboloid. And if you want to see what a three-dimensional surface looks like, well, really these days, just download a three-dimensional grapher on your phone and you'll be able to put in a function and see what it looks like. But if you didn't have that for some reason, then you can do it in kind of a really basic way, which is simplify. So for example, if I let y be equal to 0, I get z is equal to x squared. And what is that? Because now it's into two dimensions, and probably one you've seen a fair amount. What is this? So that's a parabola. If I let y be a different number, all I'm doing is shifting it up. So you can see when I make cuts for y being a constant, I'm just getting different parabolas. If I make cuts the other way, I still get a bunch of parabolas. So you can kind of see why it's called a paraboloid. So one of the ways of seeing what it looks like is making cuts. In particular, if you do the same thing except for z, then, and I'll write this in a second, you're getting what are called level sets. And I'm going to use this one to kind of look at the graph here. So if I let z equal to 0, I get a nice boring thing. 0 is equal to x squared plus y squared. What is that? The only way it works is if x and y are 0. I put in z equals 1. I get x squared plus y squared is equal to 1, which is what? This is a circle. And you can see for any positive value of z, I'm going to be getting circles of radiuses. So if over here, and I can never draw circles real well, although I do have that, if I probably wanted to, I could use the picture thing, but so these are what are called level sets. So the idea is we can see what it sort of looks like by looking at it as if we're looking from above. And this is what it would look like from above. And we can put in the values of z, see what we're getting. And you can see, well, that's basically like a topographical map. So a topographical map, which is looking at the elevation of a mountain or something like that, is going to look just like a level set. You're looking at it as if you're looking at it from the top. So in some ways, 1.8 is saying, well, these are some things you should know. A sphere comes up a fair amount. A paraboloid comes up a fair amount. And if you're not sure what it looks like and you don't have the 3D grapher on your phone, you can sort of see what's going on by looking at it from above by letting z be equal to fixed numbers. And then there are a couple others that come up. So let me just do the last couple, which is one is almost the same as the last one. And that's supposed to be everything squared. This is a cone. So it still is if I let z be constants, I still get circles, but now I instead get, and this is one of the ones I can sort of draw, I get the cone going off to infinity. And that's going to end up being something that is fairly useful for us. So that will come up also. As I said, you don't need to know these. It's just kind of nice that you recognize something so you know what shape it looks like, so you might know what's going on, but you don't need to. The last one, which I want to do, which is just kind of an introduction to the next section, is hyperbolic paraboloid or hyperboloid, whichever way you want to say it. And the reason I want to do it is if I try drawing it, I'm not very good at drawing things, but I get something like this. And the idea is if we now start thinking about things we did in Calc 1. So in Calc 1, one of the things we used derivatives for was to see when it's increasing or decreasing, to see where it's concave up or concave down, and to see where minimums and maximums are. Well, with this picture, you can see once we get into 3 dimensions or more, we're going to start getting extra types of things, which is if I look at the point right here, if I'm looking in this direction, it's maximum. But if I'm looking in this direction, it's minimum. And so we're going to get this new type of thing instead of just minimums, maximums, and inflection points. You can also get what are called saddle points. And this will be something where the second derivative in one direction is negative, the second derivative in a different direction is positive. And so it's an extra type of thing we'll get, which will make it a little bit more complicated. So pretty much that's 1.8. 1.8 is just, here are some types of surfaces that come up because they're fairly elementary and have a nice property like this last one. And you don't need to know them, you don't need to be able to draw them, but if you can, it makes picturing some of the stuff a little bit easier. So if you want to try the homework in 1.8, you can, but none of those types of questions are ones that you would be asked for directly on a quiz or test. It will only come up kind of in the background of something else, which is we're finding a tangent plane, and we're finding the tangent plane for what turns out to be a cone. And knowing that it's a cone might help you a little bit with the visualization, but it's not going to actually be in the problem. So there's the end of chapter 1. So 1.6, 1.7, and 1.8 really you can at least skip. You can skim through it if you want to get the idea, but you don't. None of those by themselves, except for the tangent line at the end of 1.6, and we'll start using that later. So I'll remind you of that particular one. Is something that you need to know. So let's, what will hopefully be the usual thing, which is what I'm going to do now, is let's quickly start 2.1. We have about 15 minutes, and we'll mainly do it tomorrow. And in some ways, this is kind of what I want to do, because 2.1 is the first of the actual calculus parts of this course. And this is what is called partial derivatives. So first little thing is, since we can now have more than one type of derivative, we can no longer just use a prime. So we're going to have a different notation. This is, let me start writing something messed up. The derivative of f with respect to x is written f with the subscript of x, or this way, where this is a made-up symbol that's supposed to look like a stylized d for derivative. So the way I usually draw it, it kind of looks like a 2, but it really is this full symbol. And it turns out that taking partial derivatives is pretty much the same as taking regular derivatives. There's just one idea that's in the background. Is what we're going to do, in some ways, typical physics thing. We're going to look at one direction at a time. So if I want to take the derivative with respect to one variable, I'm going to assume all the others are constant. So let's look at an example to see what I mean. So here's a function with more than one variable. And now I want to take the derivative of this with respect to x. And so the idea is I have two variables, x and y, but since I'm taking the derivative with respect to x, I'm going to assume y is a constant and treat it like a constant. And so in this first one, I'll do it kind of the long way, which is, you remember from Calc 1 that if you have a function and you multiply by a constant, when you take the derivative, it just stays there. So 3 stays there. Derivative of x cubed is 3x squared. Y squared is also constant, so it just stays there also. So the two constants, and I'm treating the y as a constant for this one, I just leave there because I'm multiplying. And then I take the function with respect to x. The middle one is just x, so it's just like a one variable one. And let me do the same thing here. The 3 and y cubed are constants, so they just stay there. And I take the derivative of x, which is 1. Once you've done a couple, you'll just go immediately to that this is 9x squared y plus 8x plus 3y cubed. And same idea for derivative with respect to y, except now we're assuming x is a constant. So what would be the derivative of this thing with respect to y? And again, I'll do it the long way. So now x is a constant, so the 3 stays. X cubed is a constant, so it stays x cubed. Yes, so I'm getting answers multiplying it out. So again, doing it the long way. But once you've done a couple, you will start skipping this. So in terms of formulas, there's nothing really new. So we're still using the same formulas from Calc 1. If you're multiplying by a constant, it just stays there. If you have a constant alone, its derivative is 0. If I'm taking the derivative of this, that's the same thing as what's the derivative of 4. And what's the derivative of 4? Well, it's 0. Well, since I'm taking the derivative with respect to y, x is a constant. So 4x squared is just like a 4. And you remember from Calc 1 that things are, if you multiply by a constant, it just stays there. But the derivative of a constant is 0. So this is because there are no ones. So let me do a couple others to remind you that it can get slightly more complicated, just like other derivatives. But any questions on this one? Let's do this. So, just like in one variable, we can have things where we have to use the chain rule, or the product rule, or the quotient rule. But those aren't new. It works the exact same way. So if I want to take the derivative with respect to x, what rule am I going to have to use for this first term? Right. I'm going to have to use the product rule because I have two functions both with an x in it. So I'm going to have to take the product rule, and you remember that is, whichever order you want to do it, take the derivative of the first term, leave the second alone, plus leave the first alone, and then take the derivative of the second. And what's the derivative of e to the xy? So first little thing is notice it's not just e to the x, so we're going to be using the chain rule. So just the answer was just given to me, but so derivative e to the something is itself, and 10 times the derivative, and the derivative of x times y with respect to x is y. And then it's not obvious, but my middle term is 4xy cubed. E to the xy, right? Oh, yes, thank you. I lost the y. Oh, so let's go down here. So we're looking for, that's this. So we want to take the derivative of the exponent. Derivative of xy with respect to x is, well, the y is a constant, so since I'm multiplying it just stays there. And the derivative of x is 1. So I get the y. So we have to think of y as a constant. So this would be the same as what's the derivative of 6x? Where 6x is 6. So the derivative of yx is y. And the middle one is a more basic one, like the last one. So again, the y cubed is a constant, as is the 4. And the derivative of x is 1, so it just comes down to the 4y cubed. And what's the derivative of the last term? Zero, because right, it's a constant with respect to x because there is no variable x. So let's do the same thing for derivative with respect to y. So for the first term, do I need the product rule for the first term? No, because I only have I have a constant times a function of y. So therefore, this one I can just do in the more basic way. 3x squared is a constant, it stays there. Derivative of e to the xy is, again, derivative of e to something is itself. And now what do I multiply by? X, taking the derivative of xy with respect to y instead. And then the middle one, again, is a more basic one. And what's the derivative of the last term? Although it's kind of a pain for you to write. Yeah, there it is. I'll do in the two pieces. It's 3 ln of something. It's 3 times 1 over the something, and then times the derivative of the y squared plus 1. A little thing, if you haven't had me before, I don't worry about simplification. So once you have an answer like this, you could leave it like that, even though obviously the first term is 3x cubed, and the last term, obviously, as some people wrote, is 6y over y squared plus 1. Whichever way you want to write it is fine. So as I said, there aren't really any new, for now at least, any new formulas. It's just this idea, which is when you take the derivative with respect to one variable, you assume all the other variables. So in some ways, this is why I like doing it near the end of class, because this is something you're going to have to try on your own to figure it out. But let me do one more to add in one more term. I'll go back to a simpler one. Which is, there's no reason we can't have more than 2 variables. We can have as many as we want. We can have 100 variables. Obviously, in this class we won't, because then it would just be tedious. And now we can ask, what are the 3? And then I'm going to put it together. So this is now back to a simpler one. What's the derivative of this with respect to x? So 6x. And the other two stay the same. Y cubed. Derivative with respect to y is derivative with respect to z is in definition, which will put all this together. Is if I put the partial derivatives in as a vector, I'm going to get what's called a gradient. And this we're going to be using a fair amount all through the course. It's going to give us lots of nice flow properties. So in particular here, the gradient no, so this is gradient. It's another made-up symbol, and that's called the gradient symbol. So this is the gradient, and we can ask things like, well, what is the gradient of the function at a particular point? In which case, in this here we would get this. And it'll give us some nice things. So for example, what we'll see in a couple sections is this will give us the direction that the function is increasing as rapidly as possible. And if I want to find the derivative in a 45-degree angle, I would again use this. So this, we're going to use a fair amount of. But let me do one more thing. So we got the three partial derivatives. Well, as you might expect, just like in one derivative, we can keep going. So I have the derivative with respect to x. I can have the derivative with respect to x twice, which is just the derivative with respect to x and again. So what would be the second derivative of f with respect to x? You can still read my thing. So it's going to be the 6 y z. And I can do the same thing with respect to y. I can take the second derivative with respect to y. I can take the second derivative with respect to z, which in this case is kind of boring. There's no function. I can also do mixed ones. I'll just do one of these. So that's the derivative of x with respect to y. So let's get rid of this with respect to y. And let me ask a related one. What if I reverse the order? What's the derivative of the derivative of with respect to y and then with respect to x? Okay. And it'll turn out, for us, this will always be true, that the order that you take the derivative won't matter. In really weird cases, if the function's something really weird, something a made-up type function, you can make it so they're not equal, but we're not going to run anything like that. So, end of class, this is normal class time. So what you're going to do for tomorrow is look at the quiz. This is 2.1, so if you want, you can start looking through this. But as hopefully you can see, most of it is not much new except for the idea. And there's just one type of thing that I have to throw in, so I can completely finish 2, but we mostly have. So, it's the same thing. So, so if I did, so I only did one, so there, we did 2 of the mixed ones. I could just easily do x and z or y and z. So there are, in some ways, 3 mixed ones also. xy, xz, and yz. And those work the same way. So I just ran out of room. So let me stop.